the essence of the brain, especially the human brain, is to take sensory inputs and to make sense of those, meaning cognitive sense, and then to interpret those signals. And so this may come as a shock to some of you, and by no means am I trying to be insensitive, but pain is a perceptual thing as much as it's a physical thing. So let's start our discussion about pain and sensation and regeneration and wound healing with a discussion about a very important system in the nervous system, which is the somatosensory system. The somatosensory system is, as the name implies, involved in understanding touch, physical feeling on our body. And the simplest way to think about the somatosensory system is that we have little sensors, and those sensors come in the form of neurons, nerve cells, that reside in our skin and in the deeper layers below the skin. And indeed we do. We have some that correspond to, and we should say respond to, mechanical touch. So, pressure on the top of my hand, or a pinpoint, or other sensors, for instance, respond to heat, to cold. Some respond to vibration. We have a huge number of different receptors in our skin, and they take that information and send it to our spinal cord and then up to the brain. And within the spinal cord and brain, we have centers that interpret that information, that actually make sense of those electrical signals. And this is amazing because none of those sensors has a different, unique form of information that it uses. It just sends electrical potentials into the nervous system. So the nervous system, you somehow decode what a given stimulus on your skin is. So maybe it's the wind blowing gently and deflecting some of the hairs on your arm, or maybe it's a sharp pinprick, or a hot stove, or the warmth of a glowing fire. And there's a famous case that was published in the British Journal of Medicine where a construction worker, I think he fell, is how the story went, and a 14-inch nail went through his boot and up through the boot, and he was in excruciating pain, just beyond anything he'd experienced. He reported that he couldn't even move in any dimension, even a tiny bit, without feeling excruciating pain. They brought him into the clinic, into the hospital. They were able to cut away the boot, and they realized that the nail had gone between two toes and it had actually not impaled the skin at all. His visual image of the nail going through his boot gave him the feeling, the legitimate feeling, that he was experiencing the pain of a nail going through his foot. Now, that is not to say that all pain that we experience is in our head, but it really speaks to the incredible capacity that these top-down, these higher level cognitive functions have in interpreting what we're experiencing out in the periphery, even just on the basis of what we see. So what we're talking about today is plasticity of perception, which has direct bearing on emotional pain and has direct bearing on trauma. The essence of the brain, especially the human brain, is to take sensory inputs and to make sense of those, meaning cognitive sense, and then to interpret those signals. And so this may come as a shock to some of you, and by no means am I trying to be insensitive, but pain is a perceptual thing as much as it's a physical thing. It's a belief system about what you're experiencing in your body, and that has important relevance for healing different types of injury and the pain associated with that injury. In people's pursuit for neuroplasticity, a question that comes up every once in a while is people will say, if I just brush my teeth with the opposite hand for a couple nights in a row, will I get neuroplasticity? And the answer is probably yes. I mean, it's a deliberate action. You're focusing on it. There's an end goal. You're very likely to make errors. And making errors is really important because those errors are the signal that plasticity needs to happen. And then when you get the actions correct, then those correct actions are programmed in. So think about a sprained ankle scenario or a broken arm scenario. We're all familiar with the stories of people having a cast on and then getting the cast off, and that the particular limb that wasn't being used, that was casted, is much smaller and atrophied. Most of that atrophy, you might be surprised to learn, is not because the muscles aren't being used. It's because the nerves sending signals to those muscles are not active, and therefore the muscles aren't contracting. Work done by a guy named Timothy Schallert and his graduate students and postdocs. What Schallert and colleagues showed was that if we have damage to our brain in the sensory motor pathways, any number of different sensory motor pathways, or we have damage to a limb, could be a leg, could be an arm, could be a hand, there's great benefit to restricting the use of the opposite, better performing, uninjured limb or hand or other part of the body. They had about a dozen papers showing that if there was damage centrally in the brain or there was damage to a limb, so unilateral damage, as we say, one side, the thing to do is not to cast up the damaged side, although you need to do that to protect the limb, of course, from further damage. So if it's a broken arm, you need to cast the arm or you need to brace the arm. But that the key thing was to restrict movement of the intact, uninjured opposite limb. And when they did that, it forced some movement in the injured limb. And remarkably, through connections from the two sides of the brain, through the corpus callosum, this huge fiber pathway that links the two sides of the brain, they saw plasticity on both sides of the brain. Let's say I injure my left ankle and I'm limping along or I'm using crutches. You would think, well, the last thing you want to do is injure your opposite limb or not use your opposite limb. My right ankle is perfectly fine. But if I lean too hard on my right limb and I take all the work out of the left limb, the left ankle, that's actually setting up a situation where there's going to be runaway asymmetry in the central pathways and the nerve to muscle pathways on my left side. And so what they suggested and what they showed in a variety of experiments was that by encouraging activity of the injured limb, provided it could be done without pain, and importantly, not just exercising that limb or part of the body, but restricting the opposite healthy part of the body, that the speed of recovery was significantly faster. In the brain, you have excitation and inhibition. And certain things like fibromyalgia, for instance, which is whole body pain, relate to too little inhibition. In fibromyalgia, there's too little central within the brain modulation of the pain responses so that people experience whole body pain. So in that case, the emerging therapies are really interesting. People with fibromyalgia, which is this whole body pain, are now starting to use red light therapies. And I don't think this is a field that's progressed far enough now to really place any firm conclusions on. But the idea is that red light therapy locally may have some effect in getting very bright light, red light therapy. In many ways may be approximating the effects of nature.